So welcome on this session where we see what happened behind the scene in database when you start to have an async application. It could be just a console application like I have that's just using multi-threading, or can be just a fully deployed API that just making different request database. I will start from scratch, from zero, and we will see what is inside the database, why we need to have that thing inside and understand transaction, concurrency, isolation level. And then at the end of the day, at the end of the session, we'll have a couple of tips and tricks where you can learn more about some more advanced stuff, I would say. I am a PM in the Azure SQL team. Been a developer like forever. I'm still a developer. I'm just into the Azure SQL team, making sure that Azure SQL is the best and SQL Server are the best place for developers to be. You can find all my information here. Let me highlight that the slide deck and the demo also of my other session, in case you've been to that one, are available. I just uploaded everything there, also with the source code for the repositories. And let's go directly into the topics of the day that I just mentioned in a second. Okay, so first of all, let's just start with the demo just to make it everything more easier and fun. I have an application. I created an application. It's super easy and simple. Here we go. So let me just remove all the stuff that I don't need. So basically, the application is a console application, is a .NET application. It accepts a couple of parameters. It creates a class, an instance of the class demo, and then calls the method run. The method run just do some trick to invoke the right demo I want to execute, but basically generate a list of tasks. In this case, 2 tasks. You can try also with 10, with 100. It's probably the same. And then waits for all the tasks to be executed before ending the execution path. And what is the first demo that we will be executing? That's super easy. I just open a connection using all the async method, and I don't do anything else. I just wait. And I want to see what's happening in the database engine, okay? So let me run this, and I will run everything in release mode. Now, you have just to specify which demo I want to execute. I want to run the test, the first demo.net run, okay. And now there will be just 2 connections open. Let's see what happened in the database. So first of all, there is a DMV, dynamic management view, called the session that will tell us, in this case, I'm filtering for my specific program name that I named demo. You can define the name of your program in your connection string, and I really recommend you to do that, because it makes it easier to filter out the connection are connecting to your database. And I just want to see if my application is connected. It is great. I have 2 sessions, which means that there are 2 connections active from the application. Oh, that's interesting. They're sleeping. But maybe it's OK, because I didn't do anything. So yeah, the application basically is not doing anything. So the application is connected, and SQL Server is just sleeping, waiting for something to do, right? So I don't expect to see any requests. Requests are instead the query that are being, or the requests that are being executed. I haven't executed anything, so yes, that will be probably empty. Perfect. I skipped this one. We'll discuss later. And that's it. But there is one thing that I want to show you here, logs. Let's see if there are any logs. I haven't done any transaction at all. Let's see if there are any logs. Let me just see that, yes, it's still running. Interesting. There are 2 logs on the database. So what is locked, actually? And what are locks, we will see in a second, but these are the interesting part. So we are locking the database with a S lock, and this has been granted. What does it mean? Well, let's go now back to the slide. Now that we start to have some clue of what's happening. Well, first of all, the database has been locked, which means that we are using it. And the locked with which the database has been locked with is called S, a shared lock. Means anyone can take a shared log, even if there is another one, because it's like S likes to party together. Yeah, so we can all use the database together. Nice. There are another kind of lock that we haven't seen, but I want to introduce because it's important, and you can probably also figure out that it's needed. Exclusive lock. Like, what if I want to drop a database? Well, I should take an exclusive lock, right? Because I can only be the one dropping database. So if I would have dropped a database, I would have seen an exclusive lock, which means that no one else can access the database, and the lock may be or may be not compatible with each other. An S-lock is compatible with other S-lock. So if I'm putting a lock on a resource and another one put an S-lock, be my friend. But if you want to put an exclusive lock, no, I don't do exclusive lock, because even if I'm reading something, imagine if I'm accessing something and you want to get an exclusive lock, exclusive means only for you, well, I'm already using it, so you have to wait. If you already taken an exclusive lock, I have to wait, right? So these are the two most basic locks that we use to synchronize operation and to make sure that you are still using, you can use database and no one is deleting it from under your seat, right? So this idea is extended to different objects, as you will see. But let's start to fix this in mind. Shared log and exclusive log. Shared can be shared, as the name implies, and exclusive is only for those who acquired the lock in the first place. Now, how this can help you as a developer? Well, this is something I got from Stack Overflow. It's a question. And someone using, this probably looks like a node to me, is trying to insert some tag in a table only if the tag doesn't exist yet, which makes sense, right? So I'm publishing a blog post, and I'm writing into my tags table that the blog is about X, Y, and Z, and I want to make sure that if X already exists, I don't insert it again because maybe it's just a duplicate, maybe I get an error. So the question on the Stack Overflow was, is this right? Or, yeah, I'm summarizing it, because sometimes it happens that I get errors if I have a primary key, or if I have duplicate, if I don't have any key that is protecting me for having duplicate data. Because what happens if exactly the same request, since as you can see, this is most likely a REST API, is executed at the same time more than once, right? Well, it could happen that between this select that tries to figure out if what are the tags in the table, and the insert, someone execute an insert. So the selector contains all the data, right? Well, that's a huge problem because we need to be able to protect by our application by having this kind of issues, because otherwise our application can randomly crash or just add bad duplicate data, which is probably even worse. So that's why we need transactions. Transaction guarantees that a certain set of data, and then we'll discuss in a few which kind of set, are treated as a all or nothing operation. Everything works, or nothing is done, and everything is returned to the initial situation. You probably have heard of this acronym yet. ACID, atomicity, consistency, isolation, and durability. I will not go into detail, but basically it's several properties that your transaction are that guarantees you that, again, you can do all or nothing. Now, by default, a single command, and before we saw two commands, a select and an insert, right? So I'm saying a single command, so the single insert, the single update, the single delete, even the create index are transactions. So if I delete 10 rows using a single delete command, that is a transaction. Or I can delete all the 10 rows, or I cannot. If I cannot delete even just one, everything will be undoed, or more correctly, rolled back, which means I still have all my rows, right? That's for one statement. But maybe, like in this case, in the sample, in the application sample case, I have more than one statement. So in that case, I need to open an explicit transaction. My transactions are opened as a begin run command. Then I can write other bunch of commands, and then I can commit or roll back. Within this begin and commit or roll back, everything is treated as if it were logically one operation. No matter if you have 1,000 insert, or insert, update, delete, and many other stuff. You're saying that logically, that is one operation, and therefore must be atomic, consistent, isolated, and durable. Now, that's interesting, because what you need to remember is that by default, explicit transaction, the one that you open and manage manually, don't roll back if you have errors. So if I open a transaction, do my stuff, and at some point there is an error, it doesn't roll back automatically. It's up to you, developer, to decide if you want to undo everything or move forward and commit what has happened so far. this is tricky. It's a super important part because I've seen many storage procedure and a lot of code just thinking that within a transaction, everything is automatically committed or rolled back, and this is not true for an explicit transaction. And I'll show you in a second. But you may be wondering why I really want to not undo what I'm doing, or what I want to do something more complex and just undo everything and retry and retry it. Well, exactly for this is a latter example. Maybe you want to retry it. Let's say you have an error that you think like a deadlock, then you know it's transient, so you want to catch the error and retry it, right? Instead of just erroring out and undoing everything. So that's why by default, your explicit transaction must be terminated by or a commit or a rollback, and you are the one in charge of deciding if to use a commit or a rollback. Now, it's super important if you're using Java and your JDBC driver, that JDBC uses a specific option that is called implicit transaction. Implicit transaction means the driver opens the transaction for you, even if you have a single command. So it always assumes that you have more than one statement, and will not commit automatically. So you have, even if you are executing a single transaction with JDBC, and by default, as far as I know, the implicit transactions are on, you need to commit, even if you never issued a begin transaction. So if you are using Java, make sure that you take a look at the JDBC and implicit transaction. There's several articles on the web that explains you exactly what does it mean. But in general, it means what I'm going to show you right now. So let me go here and let's go to the transactions and do something super simple. So first of all, I have my simple table here that contains timesheet data, and there are no rows with ID greater than 10,000, right? Perfect. Now, let me try to add some rows here. And I'm executing everything, the insert, so every single row is executed as part of a single command. With an insert, only one statement, I'm inserting or trying to insert 4 rows, okay? So this is one command, which means that is automatic committed or rolled back. Now, please note that the last 2 items have the same primary key. So this is going to fail, right? But the first row will go, the second will go, the third row will go fine, the fourth one will generate an error. So the expectation here is that for what I have just said, that at the end of the day I have an error, and still, once the command is terminated, there are no rows in the table, which is exactly what you expect. Perfect. Now, what happens if instead using this technique to insert 4 different values, I use 4 different statements? Well, let me do exactly the same. So I'm inserting the same 4 rows. The last 2 will have a primary key violation. Now, one row affected, another row affected, and so on. The last one generated a primary key violation. What we have here, well, again, 3 rows, because each one is as a transaction on its own. Here we didn't put everything together in a single transaction, right? And again, this is probably pretty much expected if you have some experience with relational database and Azure SQL specifically. Now, let's do what we think is good. Begin a transaction. So I've cleaned up the mess I've made. Now let me try again. This time I start a transaction, right? Start a transaction, insert the data in my timesheet, and then I stop here because I haven't closed the transaction yet, so the transaction is still open. I have inserted 3 rows, 1 generated an error. How do I know the transaction is still open? Because I can use trunk count, and it tells me there is a transaction. Good, I'm happy. Let me see the data. Well, first of all, why I executed this statement right now? Because I want you to understand, that's super important, that the changes you do in a transaction that you started are visible to you, right? If I would have another connection, well, we'll discuss what will happen. But I'm seeing the transaction I've made. So I see these 3 rows inserted. Still, I'm in the transaction, right? Now, if I commit the transaction, this means that I'm OK with this outcome. I'm OK having only 3 rows instead of 4. Because I'm responsible for deciding if the transaction needs to be committed or rolled back. If I commit, well, then I have the 3 rows. So keep in mind, and this happens also within a storage procedure. If in a storage procedure you just have begin run, commit run, and no other options or exception management, this is what happened. You commit the error. You say, I'm fine, I did something wrong, I'm still okay, so just let's go with it. If instead what you want to do is really say, or everything inside the transaction works, or you automatically roll back and close the transaction, then what you have to set, again, this is something possible inside a storage procedure, is set exact abort on, which means as soon as there is an error, I'll roll back everything. So if I do this here, and now do exactly the same error, exactly the same code, and stop here, now I have the 3 rows affected, the last one is generating an error. Let's see how many transactions I have, 0. Because the rollback happened automatically, okay? And in fact, now I don't have any row at all, because that was an entire transaction, okay? So it's important to understand that explicit transactions are something you have to manage. Now, what we learned very quickly, again, that from the same connection you can see the data you have changed, and someone may also come up with the idea, well, that's great. So maybe instead of opening another connection, let's say I need to see the 3 rows, I can inject another thread in the same transaction. That's going to be a very bad idea, because you actually want your transaction to be isolated. Why? Because until the data is committed, doesn't really exist, right? So if it doesn't really exist, you cannot take any decision on the data because it may be rolled back. So you want your transaction to be isolated. You want another connection not to be able to see the 3 rows until you decide to commit them, or roll it back if you want to roll them back. So that's why we need locks. And that's why that's how transaction and locks are related to each other. Locks are used by transaction to guarantee isolation and avoid inconsistencies, right? Now, to be honest, the only way we can absolutely avoid any possible inconsistency would be to never allow 2 transactions to happen at the same time. That's called serializable level. So if you serialize access to all the data, well, of course you don't have problems, because there is no one that is reading what you are modifying, right? That's not good for concurrency, as you can understand. So it's very bad, for example, for REST API if you are creating a REST application. So you want to basically be able to define how much you are protected against the error that can happen or the inconsistencies that may happen using what is called the isolation level. There are 4 isolation levels we'll discuss later, and they are all helping to define what kind of inconsistencies you will be avoiding. Lost updates, for example, it's let's say you do update column equal column plus 1. Well, you don't want between you read the column and update the column someone to change the data, because it says if it changed the data and you were not aware of that change, let's say the original value is 1 and you expect it to become 2, but what if someone changed it to 5? Well, you read the data when it was 1, now you are updating it to 2, so you have a lost update, because basically you are overwriting the data that someone has changed already while he was in a transaction, because you also started to read and write on the same transaction. That's bad, 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 right? This caused death of people due to a X-ray machine. It's also documented in Wikipedia due to this kind of concurrency issues, right? Now, we don't want to do that. There are other problems, and in the article that I linked at the end of the session, you can read all details, but dirty read is basically when you read data that is uncommitted. So you say, oh yeah, I'll go and get all the money from the bank, you have $1 million money, and then someone roll back the transaction, I have 0. I'm happy, the bank a little bit less. So inconsistent analysis, that is what we are going to resolve right now. Like, inconsistent analysis is the problem that the REST folk that was creating the REST API encountered. I'm reading something, and based on what I read, I take some action. What if between what I read and my action, the value changes? I cannot read the same value again. So it's an inconsistent read or inconsistent analysis. It's also called non-repeatable read. And then you have phantom reads, which is basically when you read data that doesn't exist anymore at a certain point. Insert and delete typically. Now, let's not go too much into detail, but I just want to understand you that there are several different anomalies that can happen when you have concurrency on the same data, where not everyone is reading, but someone is reading and someone is writing. Now, the isolation level is what allows you to simply focus on what kind of inconsistency you want to prevent, without having to figure out what locks are needed. The engine will figure out what locks are needed and for how long are needed. And this is specifically important. Let's see why this is so important. Before going to the demo, I will be using the default transaction isolation level. So if you start up an application, Python, C#, doesn't really matter. The default is read committed. Read committed means I can only read the data that has been committed. So if you begin run, insert something, another one in another connection tries to read the data, they will not be able to do. They will be either locked or will read something else. And we'll see later what. So this is the default for SQL Server. For Azure SQL, it's still the default, but implemented in a different way. And we will see what is the different in a few. Then we will be using a repeatable read, because I want to resolve the problem at the beginning. I want to be able to do a repeatable read, means I select from my table, and then when I come back and select again, I want to see exactly the same data, right? And then serializable is basically the highest, where you say, I only want to have exclusive access to the data because I want to be protected by any possible inconsistency. You can also have another version of serializable called snapshot. We will discuss it later when we will discuss about locking versus versioning. Now, let's take a look at what happened inside the database when you start to have transactions and queries running in the database. So I'm moving and using the demo number 2, where basically I'm just opening the connection. I'm not still opening a transaction, okay? So by default, I'm in this auto commit mode. I open my connection, execute a simple select where I get from 1 to some thousand rows, and we see why I want to see the difference between getting 1,000 and maybe 1,000,000 of rows. And I will print it, and for each row, so I'm getting a reader. For each row I get, I print it in the screen, and I wait something between half a second and half a second and a half. So I'm slowing down my application. I want to see what happened in SQL, okay? Let's do it. .NET run, and let's say I want to just try with 1,000 rows. Okay, so it's reading 1,000 rows, started to read here, and every read will take a few seconds, so we are good to see what's happening here. Let me close this. Let me just take a look at the demo here. So first of all, let's again take a look at the session. We have only 2 sessions, so 2 different connections from the same application. Great. It's like, when I say 2 different connections, it's like 2 different people that they don't want to talk to each other, right? 2 completely different and isolated transactions, potentially. Now, there is a select running, right? A select is a request by application, so you probably expect to see something here, right? Ooh, that's nothing. Interesting. Maybe the application stopped working, it's still running. So SQL is executing something for which there are no requests. That's weird. OK, let's see if something is waiting, because actually my application is forcing some waits, right? So I would expect here to see some waits. Actually, there are some waits, but are not the one I expect. And actually, there is literally no wait here, right? It's 0 and 1 millisecond. So this is more like metadata information I'm getting. Let's see the logs at least. So something should be locked because I'm reading. So at least the table should be locked because no one can delete my table while I'm accessing it, right? OK, that's weird. There is no lock on the table. Still, I'm connected. The application is running. Yes. So what's happening here? I only asked for I only asked for 1,000 rows. My select is already done. The engine already did the select. Now, the only thing is waiting is sending the result buffer to my application. Since my query is so small and there are no additional requirements from my side to block the rows once I read the rows, well, the rows has been read. Now they are just sitting in the TCP buffer to be sent out. So I don't see anything. Literally, my query is finished in this case. Now, that is completely different of what is going to happen the moment, the moment I stop my application and say I want to have 1,000,000 rows. Okay? I'm returning way more data. Let's see what happened. Okay, starting to read, still the two session, fine. Request, let's see, there were nothing. Oh, now there are two, interesting. And the query now is suspended. So the selector now it's there, because it needs to read much more data than before. So it cannot just read everything and say, OK, I'm done reading the only 1,000 rows. It's peanuts. I probably read it in one operation. And so I can just now transmit the data. Here, I need to read more. So I need to keep a task or a request open. Why they are suspended instead of running? Well, because, again, I am slowing down the usage of the result. So if my application is slow to process the result, well, SQL Server has to say, OK, my TCP buffer is big like that. You are asking me to send that much data. It cannot fit in the buffer. I have to wait. I have to push back. Like, wait. You're asking me data. I'm providing you as much as I can, but you can't consume it. So async network I/O means my query is slowed down by or the network, in this case it cannot be because it's on my machine, or the application that is not able to consume my data quick enough, okay? Let's see the logs now, because now my table is used, right? There is a transaction going on, a request. Well, something interesting we have here. Of course, we have a database that is locked in shared mode, but then we also have an object. Oh, sorry. We also have an object, and the object is, if I go and take a look at the sysobjects table that tells me all the objects in my database, I will see that this ID is exactly the table. So my table is locked with an IS lock. What is that? Why I? S is shared. I means intent. I'm not locking the table. But if you start to ask something that we'll see later, I may need to lock the table. So what SQL Server is doing is telling to itself, look, in future, I may need to lock this table. Keep that in mind if someone tries to lock the table to avoid deadlocks or situations that will be very hard to resolve. And if just I know that the intention could be to lock the table, I could prevent that kind of issue. So an intent lock is some kind of information for future improvement, for future, let's say, strategy, future in the sense that it's not that we need to still implement it in the engine, is the engine telling itself, look, in the future you may want to do this, so be prepared. So what we are really interested in is this S lock here that has been granted. And let me highlight this row, is taken on a page. What is a page? Well, you know that rows are not read one by one or saved one by one in our file. It's saved in a file, an MDF or NDF file. The file is divided in pages, and pages contain rows, like a book. So when you have a book, you have a list of rows in your page, right? Each one containing some content. Perfect. So that's exactly what the SQL Server is doing. It's reading the page that contains your data, the row that we are showing here. So every time it needs to read some row, it has to read the page. This means that the page needs to be locked. And once I finish to read all the row in the same page, I can release the lock, and then I will lock another page, right? So that's perfect, because this means that it's just efficiently locking not the single row, but the entire page, which may not be that good for concurrency, but there is a good balance. Because if I'm reading, let's say 10,000 rows can fit on a page. I could lock a page paying a small amount of memory, because every lock costs CPU and memory. Or the other option is that I could lock the single row. But if it's 10,000 rows, I have to pay the small memory amount and the small CPU usage for 10,000 times, which becomes big. So the engine tried to smartly balance between the size of the lock taken, in this case the whole page, and the memory and the resource consumed. Right? So we try to balance between concurrency and resource usage. You will see probably if I now execute this was 6310. If I execute this again, this is probably going to change because it moved, yes, to another page, right? So I finished to read all the rows in page 6310. Now I need to read the next page to get the other rows. Perfect. And as you can also see, there are two sessions here because they have two connections. They can both block or lock and acquire an intent shared on the table, for example. And of course, on the database. Metadata is just because the user I use to connect my application to SQL Server, of course, cannot be dropped if there is some connection using that user, right? Cannot drop a user if there is a connection using it. So this is what is happening inside the application when I don't have transactions, and my transaction, or at least I have an implicit transaction to be an auto-commit transaction to be more precise. And this is the read committed snapshot. Now, why the page is locked, and then the lock, once the page is used, is removed? Because the select is still running, right? Well, because we only asked by default to have the read committed isolation level. Read committed means you can only read the data that has been committed. So once you have read the data, there is no reason to keep the lock. There is no reason to block someone else that wants to change the data that I have already read. Because you didn't ask me to make sure that if you reread the data, you want to find exactly the same value, right? So I'm reading a row. Let's instead of talk about pages, let's make an example using a row. I read row 1. It was committed? Yes. I read the name, Davide, perfect. Why should SQL Server keep the lock? And in fact, it doesn't. The lock is released. This means that you can go to row 1, update the name, and then if I go back and reread the row 1, I will find another name, not mine. Now, if you want to prevent this non-repeatable read issue, you need to move your isolation level to a bigger one, to a higher one, called repeatable read, for example, which is exactly what you need if you want to do something like select from a table, do something, and then update the value you selected before, right? So in your application, you say, OK, I understand that now. So let's begin a transaction using a repeatable read level. And again, select for now. I don't want to do all the complex stuff that the sample was doing. And I do exactly the same again. Okay? So let's see what happens once we do that. So let's go to the demo number 3. This is my demo number 3. And then let's just use 1,000 rows for now. OK. Now, again, I will not go into the session at the moment because I guess you now understand that there are 2 sessions here. Let's see how many requests do we have. Nothing, again. Well, because the read was so fast that the query is basically finished. We just have to wait for the TCP buffer to transmit all the data, right? But we need to keep the locks until everything is, the transaction is done. Now you see key lock. Why? Well, you are requesting that until my select is done and transmitted completely to my application, you don't want anyone to change your data. Anyone. So we need to take a key lock, which is a row lock, basically. For each single row I am transmitting you, we need to block it and prevent that someone can change it. So we are keeping S lock. So the lock works not only in sides, like S or X, or the size of the object you are blocking, but also over time. We are extending the lifespan of this lock to make sure that no one can change what I'm reading while I'm reading, right? And that's a key, that's super important, because the moment we understand that, you immediately understand that the less transaction you manage on the code, the better it is. because now I'm foreseeably slowing down my code, right? But this is just to show you that the more code there is between when I open a transaction and use it and commit or roll back the transaction, the more the locks need to be taken, and the more it needs to be alive and working. And of course, the less concurrency I am allowing in my database to be, because, for example, I cannot go and just update one of the row right now. So it's super important. And of course, what we try to do is, again, balance between how much memory is needed to lock all the rows and how much memory it's needed to do everything else, like executing your query. That's why if I move to 1 million requests, to 1 million rows to be sent, the lock will be completely different. You will see that there are page locks. We are locking not the single row, but the entire page, which means we may even lock rows that you don't need. But still, we need to balance between how much memory we use and how much lock we actually have. So that is what is called lock escalation. It's done automatically, it's documented. By default, if you have 5,000 items locked, we escalate to the biggest, to the next bigger item. And that is made to try to, again, balance between resource usage and concurrency. Now that this is clear, and let's go here. And so what we just learned, the longer the transaction, the longer the locks are held. And of course, I told you that X is not super friendly with other locks. So even if you are doing an insert or an update or a delete, it's even worse, because no one else can read, right? The item, it could be a single row, it could be an entire page, it could even be the entire table. So make sure that you try to follow this path, this sentence. The shorter the transaction, the better. The shortened transaction possible is the one you don't do in your application. The shortened transaction is the one you completely push onto the engine. So if you can use a tool, could be SQL command with a storage procedure, it could be EF core with batching mode enabled, which is by default it is. Make sure that you don't begin transaction and do stuff and commit transaction in your application if you can, but you just send all the transaction, all the commands, begin transaction, your command, commit transaction, or rollback transaction, as a single batch to SQL, so that it can resolve all the transaction there. Because between a begin tran and the next statement, for example, there is no delay, there is no network delay, right? So this is really super important to have not a performance system in terms of how fast a query can run, but how many query can run at the same time. So this is super important from a concurrency perspective. What we learned SQL Server can lock? Well, there are many locks, but these are probably the most common you will see. The entire database, which is obvious, the page, the key if you are using a table with an index, or the row ID if you're using a heap, for example. Metadata is, for example, to lock users to avoid someone to drop a user while he's actually using something. Now, locks are probably good, but of course it's bad for concurrency, right? That's why both SQL Server and Azure SQL supports something else other than locking to preserve isolation. It's called versioning. It's way more expensive, luckily not on today's machine, but it's what you want to use. Because versioning means, well, to isolate you from what is happening and what someone else is doing, or I block you, or I give you a snapshot of the data that existed before someone started to change it. Because the rule is read committed. So I am reading a row. The only thing I care is that the value I am reading has been committed by someone. So if someone else has started a transaction, changed the value I'm trying to access to, but didn't commit the transaction yet, I can be either locked, or I can say, I don't want to be locked, just let me read the value before it was changed in a transaction by the way that has not been committed, so I don't want to read it. So with the row versioning, we need to keep the previous version of the rows, and when you try to read something that is locked, instead of stopping you, we will just provide you the previous version. which is the last committed one, which is perfect. So we are fully into the read committed requirement that you specified. By default, SQL Server 2022 uses the lock for compatibility reason. Azure SQL use versioning because we can be a little bit more free with new data coming in the cloud. If, and my suggestion is, if you can, and if you are starting a database from scratch in SQL 2000, whatever, because versioning started to appear in 2005, so any version you have of SQL Server supports it, use read committed snapshot. Snapshot is a keyword to say, don't use locking as a way to protect me from inconsistency, but use versioning, okay? And if this probably is not applicable, hopefully, anymore, but if you are still using no lock, which is a hint that you can use, or maybe you may see it in your code, don't use it anymore. No lock means don't honor locks, which means I don't care if someone is changing everything and then undoing it, I want to read everything, which means you have the potentially dirty read things because you are reading data that technically does not exist because it's not yet committed. Okay? So no lock is equal to read uncommitted. Is the opposite of what it says. I don't know why we had the brilliant idea to call it the opposite of what it does, but that's it. So just make sure that you don't use no lock anymore. If you want to be not blocked, but still consistent, use read committed snapshot. Now, having said that, let's go and take a look here. Still have 10 minutes, so let me just show you this, and then we're good. Let me, yep, still here. So I'm using a new table just for the sake of avoiding to have to reinsert the data I'm going to delete right now. And I'm beginning a transaction, and well, I will check that the transaction has been open. I'm going to insert some data, completely delete all the projects marked alpha, update the project marked bravo, and see what happens. So begin transaction, do all my insert, delete, update. Then from the same transaction, I want to see the result of my changes, which I will be able to see. And then I want to see how many transactions I have. Perfect, I have one transaction here at the end also. So everything is in a transaction. This is the content of my data. Now project alpha is gone because I deleted it. And in fact, if I do a group by, I see that there is only project bravo and the new secret project I started to work on. Good. What happens if someone goes and open another connection and tries to execute something like select from the table that I changed, but still not committed, and see what happens. Well, first of all, let me make sure that we are in the right isolation level. So by default, read committed snapshot on is off. So we are not using in SQL Server, which is where I'm connected right now, the versioning. So let me execute this. Is waiting. And if I go and check what is happening on the logs and everything I just explained, you will see that actually, let me do two things separate, so it's better for you. I can use a query on sysdm tran logs that says, hey, session is requesting a lock on this resource ID, but I cannot grant it because it is requesting an S-lock. Someone put an X-lock, you just wait. Now, how do you not have to remember all the DMVs and views that I just mentioned? Go and download this storage procedure called SP who is active that will give you full insight of what's happening inside your engine, and it will tell you, look, this is your query, right? Yes, thank you. Now, it's, where is this now? Yeah. I closed it, okay, let me open it again. Okay. So this is the query, nice. This is another way you can understand what's going on, is waiting from the lock manager to get an S-lock, which is exactly what we saw before, and is blocked by session 54. What is doing session 54? It's this one here. Aha, someone opened a transaction and didn't close it. Cool. Okay, so SPU is active, simplifies your navigation within all the system table that we use to show you exactly what's happening inside the engine. We don't hide anything. The engine is completely transparent. Of course, there are many DMVs that you need to know, but SPU is active will make super easy for you. So having said that, I don't want to wait, right? So let me undo, and let me close this too, because I don't have enough space. Let me go here and roll back my transaction. Now, what I want to do is say, okay, I'm fine, I don't want to wait. I just want to see the version of the data that has existed when it was committed the last time. So let me go and alter my database, the current database, set read committed snapshot on with rollback immediate, which means apply the change immediately and roll back any existing transaction if needed. So everything has been rolled back, nice. I, for this reason, need to re-execute my statement here, and let me stop here again, where I did all my changes. I'm still in a transaction, right? I'm still in a transaction, yes, I am. And now here, let me try to read my data again. Aha, now I have the alpha. And I can easily do everything needed. I don't see the secret project because this is the snapshot of the latest committed data, and the other transaction didn't have done the commit yet. So I'm just seeing the committed data. Now, what happens if I commit my transaction here? Well, now if I go here and I execute everything, I have the new data. You may tell me that's a non-repeatable read. Yes, it is. Because I asked by default to be in read committed, right? Repeatable read is a higher transaction isolation level that I should have chosen if I wanted to preserve my, my reads from someone else changing the data, committing the transaction so that I don't see two different things when I read once and read twice after someone else committed a transaction. So this is to tell you that you have all the option to basically decide what is the right transaction isolation level for you. We start with the recommitted because on average is the most useful and probably the best one that gives you enough consistency and enough concurrency. By default, in Azure SQL, we use versioning to prevent to prevent inconsistencies due to non-isolated transaction. In SQL Server, we use locking for historical reason. Change it to versioning if you are creating a database from scratch. How do we now solve the original problem? Well, first of all, before going there, you may tell me, you know what? I really don't want locks, because no matter what, the locks really sucks, in the sense that they bring down concurrency, right? So if you want to completely avoid locks, go and use in-memory tables, which look like tables, they are not tables. But they completely look like tables, they behave like tables, they can be used by like tables. The difference is that we completely rewrote that part of the engine for this specific memory-optimized table, so that we only use raw versioning, or something called MVCC, multi-version concurrency control, so that we never take a lock, never. And you can go up to 5 million transactions easily per second, which would be unreachable using normal tables on current hardware, right? So here it's like the details of the in-memory lock-free table. Tip and tricks, you need to keep the transaction short. So one good way to do that, instead of handling the transaction in your application, why you don't take all the data that needs to be changed, maybe the order header and order details, pack it into a nice JSON payload, send it to Azure SQL or SQL Server. On SQL, you have all the options to open a JSON and get all the data that you want, so that you can do the transaction in the storage procedure, which means that you move the data over the network, no transaction open. When you call the storage procedure, now the transaction starts, but everything happens inside the storage procedure, so it's super fast. If you don't want to use storage procedure because you're using an ORM, like EF Core supports batching. So it should do this already for you. If not, make sure that you have configured it correctly. By default, EF Core, which is the latest version of Microsoft ORM, does that already. Of course, you can decide how big is the batch and everything else, so here there are the links. But it's super important to understand that you should not manage a transaction in your application if you can. And that's the idea of the JSON. JSON is everywhere today, so you have the front end is communicating with JSON to the back end. Why your back end shouldn't communicate to your database with JSON? We can, it's fast, it's very fast, and so just do it. To solve the first problem, the insert if not exist, there are several ways. Here is an article I wrote to go in all details to tell you exactly how to solve it. The formal, correct solution would be to use a repeatable read, but we don't want to have repeatable read because it basically prevent the concurrency we want. So you have a little tweaks called lock hints that you can use to make sure that you lock only and exactly what you need without taking any bigger lock. So I lied at the beginning when I told you you don't manage lock. If you want, you can. It's not that I'm recommending. So use the transaction isolation level by default. If you really need to tweak the performance, you can even tell SQL Server and Azure SQL what lock to use. And this is exactly what I'm doing here. OK, I am done. I have to remind there is another slide for the bulk insert that you can find then when you download. I have to remind you, it's gone. Yeah, that the raffle is now after the next session at the 3:40 break. So make sure that to attend. And any question? Just one option. Oh, OK. I can take a question offline since there is a next session coming up. Make sure to evaluate the session. And thanks. I hope it was interesting. Thank you.